Welcome everybody. So my name is Abu Nasir Masud, and I am going to talk about how we can analyze software code using artificial neural networks. So program analysis or software analysis can be categorized into three main classes. So first one is the static analysis. It is a kind of analysis which infer program properties without executing the code. And typically program properties are inferred from a mathematical model of the code, capturing well-defined program semantics. So static program analysis are now much more mature and is being deployed in the industry. Some examples of static program analysis are data flow analysis, abstract interpretation, formal methods, model checking, separation logic, and so on. Dynamic analysis is a kind of software analysis that basically executes the code on a real or controlled environment. And typically code is instrumented and various instrumentation parameters are monitored dynamically to infer program properties, runtime program properties. So other dynamic analysis includes, for example, search-based program analysis, testing, or symbolic execution. Symbolic execution is an interesting kinds of analysis that sits in between static and dynamic analysis because it executes the program but on symbolic data. So the third kind, which is neural software analysis, it is a rising trend to solve many software engineering tasks such as code clone detection, code summarization, code smell detection, and so on. And almost all neural software analysis uses supervised machine learning techniques. That means they need a lot of level test data, and major efforts for neural software analysis then it directs towards investigating how to represent the source code to fit to the neural network model. So in this talk, I will just give an overview of these techniques, mainly how we can represent the source code and what are the kinds of neural network models that we can use. So many software analysis concepts based on statistical machine learning came from the literature of natural language processing, basically. And these analyses have a strong theoretical basis. So the naturalness hypothesis provides an important observation of why software code analysis can be done using artificial neural networks. And this hypothesis came directly from a similar observation in natural language processing, which says that most natural utterances in practice are quite regular and predictable, and they can in fact be modeled by rigorous statistical methods. So naturalness hypothesis is a similar observation in the software engineering domain, which says that programming languages are complex, flexible, and powerful. However, programs are typically developed by human developers, and they often write simple and repetitive code. The software code has predictable statistical properties, which should be inferred by statistical language models and are leveraged for software engineering tasks. And probabilistic or statistical language model is the basis of neural software analysis. So in this model, given any sequence of code tokens, for example, S1 to Sm, the idea is to infer the probability of this sequence, which is computed as a conditional probability of the token with respect to its previous tokens. And these previous tokens, we call it contexts. So it can happen that the context is very big, and then it may be impossible to compute this conditional probability with respect to the context. In such case, basically, we approximate this computation by limiting the size of the context. For example, the conditional probability of Sm in this case, this is computed by limiting the context, which is limited to n-1 in this case. So this is the basis of many neural software analysis. Now the question is, which problems are suitable to solve using machine learning? So not all problems are suitable, because static and dynamic program analysis are very good at solving some of them. some of the problems in the software engineering and program analysis domain. So to answer these questions, we need to consider three dimensions of the problem space. The first dimension is the well-defined problem formulation dimension. So many program analysis tasks have well-defined correctness criteria or a specification. For example, an analysis that type checks a program, the rule of type system defines whether the program is type safe or not. But there are problems like, for example, code search based on natural language query, code completion based on partially written code, or predicting whether a code change may introduce bugs or not. They are not well defined. All solutions must be verified by the developer, and the quality of the solutions depend on finding suitable heuristics, and machine learning models are very good for doing that. The second dimension is the fuzziness of the available information. So traditional program analysis, they are good at drawing logical conclusions from inferred analysis facts, but these analysis fail to reason about uncertainties. And neural software analysis is good at handling fuzzy inputs. So more fuzzy implies that more suitable to handle it by machine learning models. The third dimension is the amount of data for training, and neural models are data hungry. So neural software analysis works best if there are plenty of examples to learn from. And typically training an effective neural model requires at least several thousands of examples in many different forms. For example, code snippets that can be extracted from a large code corpus. So to answer the question of which problems should be solved using machine learning, we can consider those instances of the problem. So those instances of the problem which do not have well-defined correctness or specification criteria and have high degree of fuzziness and have plenty of data to learn from. So a typical conceptual framework for neural analysis of software consists of the pre-processing, training, and prediction phase. The pre-processing phase basically prepares the data to feed into the neural network model. The training phase uses the data to learn various parameters such as weights and biases to control the behavior of the model. And the prediction phase usually predicts the program properties on unseen code samples. So as I said before, practically all existing neural software analysis use some form of supervised learning. So selected code samples have to be labeled. And in order to do that, lightweight static analysis is often applied. For example, tokenizer, which is available in the compiler framework, it transforms the source code into sequence of tokens, or parser is used to transform the code into abstract syntax trees. A neural analysis that predicts types can learn from existing type annotations, or predicting code edits can learn from edit histories. So this kind of static analysis can be used to label the training data. And because large amounts of labeled examples are a prerequisite for effective supervised learning, so most neural software analysis tasks basically done so far they are basically based on the availability of the sufficiently large data sets. So some neural models, since neural models, they reason about vectors of numbers. So the most important design decision of a neural software analysis is how to turn the code samples extracted in the previous step into vectors. The most simple but effective and popular technique starts from the sequence of code tokens and map each token into a vector. So this is this kind of technique is mostly used in natural language processing, and some of those techniques are also employed in source code analysis. Other techniques leverage the fact that code has a well-defined and unambiguous structure, such as abstract syntax trees or control flow graphs, and so on. And these techniques maps the nodes of such tree or graph into vectors, and then they aggregate those vectors to yield a representation of these of the graphs or the trees. We'll see a few of them later. So the main advantage of this graph-based vector representation of code is that they provide the rich structural and semantic information which are available for the code. Uh, but the disadvantage is that graph-based representation of code are less portable across programming languages, and they are also quite expensive computationally than sequence-based models. So once the source code is represented as vectors, so the next step is to feed these vectors to an artificial neural network model. So neural models of software typically consists of two parts. One part summarizes the given source code representation into a more compact representation. For example, a single vector maybe, and then the other part makes a prediction about the code. So if the source code is represented as a vectors, and these vectors represents tokens, then the simplest way to summarize the code is to concatenate the vectors that describe the code and map the concatenation to a shorter vector using a feed-forward neural network. So this is the most simplest approach. But there are other kinds of representations. For example, source code can be represented using sequence of token embeddings, that means sequence of vectors. In such case, we can employ recurrent neural network or transformer. So recurrent neural network in this case traverses the sequences only once, but the transformer, it iteratively pays attention to a specific element in the sequence, and where to pay attention to is learned during the training phase. We have other kinds of program representations like abstract syntax tree-based representations, and for such kind of representations, tree convolution neural network is good, which traverses the tree from in a bottom-up manner. And what happens is that the vectors in, for example, in the child nodes are aggregated in the parent node, and then the root node represents the whole source code. Most sophisticated of today's techniques are the graph neural network, which operates on the graph representation of the code. So if a graph representation is given that contains initial vector representations for each node, then in the training phase, what happens is that the vector of a node is basically learned from its neighboring current states of the node or neighboring vectors of the nodes, and this information is propagated across the code elements. So this graph neural network is very good at capturing deep program semantics. So once this summarization is done, then the next phase is the prediction phase. Neural models of code are almost exclusively classification problems. For example, one common prediction component is a binary classifier that asks whether a piece of code is correct or buggy, or whether a code is a clone to another code or not. Other kinds of classifier exist. For example, an n-array classifier that predicts the classes of a code element or a code sample from a predefined or fixed set of classes. For example, predicting the type of a variable out of a set of common types. Such classifiers basically output a probability distribution over the available classes, and this is done by passing the vector of the earlier layers of the network to a softmax function. Some neural code analysis predicts sequence of vectors such as sequence of code tokens. A common neural model for such task is an encoder-decoder model, which combines a sequence encoder with a decoder that predicts a sequence. In these models, the decoder output at each step, the decoder's output at each step is a probability distribution, for example, across possible source level tokens. And training and querying neural models of the software works just like in any other domain. For example, the weights and biases of various functions that controls the model behaviors are calculated by optimizing those functions based on the examples of the inputs and the expected outputs. As for example, an n-array for the n-array classification model training will compare the predicted probability distribution to the desired distribution by a loss function, which can be a cross entropy, and then try to minimize the loss through a stochastic gradient descent. On successfully trained, this model can predict about unseen code. The final component of some neural software analysis basically validates and ranks the prediction made by the neural model, but this is optional. I mean, not all analysis is they do these validation tasks. And for example, the prediction of a model that suggests a new code, it can be validated for syntactic correctness using the grammar of the programming languages. Another example is that the prediction of a model that suggests the types of variables, it can be validated using a type checker, and this is done to ensure that only type correct suggestions are provided to the user. Then the outputs of this prediction, sometimes they are also ranked, and this ranking is done using the numeric vectors predicted by the model. And this is possible when, for example, the predicted output is some kind of probability distributions, and then they are ranked based on their probabilities. So these are these three steps, like for example, pre-processing, training, and prediction. These are the three typical steps for neural software analysis. And then, as I have told before, that the most sophisticated design that we have to do for source code analysis is how to represent the source code using using numeric values, using vectors, numeric vectors. So many neural software analysis utilizes the natural language information embedded in the code, such as, for example, the name of the identifier or the method name, or the source code comments. So such natural language information is transformed into vectors using successful techniques that are used in natural language processing. For example, word2vec. Word2vec is a technique developed by Google in 2013 that learns the distributed vector representation of the words using shallow neural networks. This is called distributed representation because the meaning of the word is distributed over several vectors. That's why it's called the distributed vector representations. And two such shallow networks that are used to learn the embeddings are called skipgram and common bag of words. In the common bag of word model, the distributed representation of a word is obtained. For example, here we want to obtain the distributed representation of a word vi that is obtained from the surrounding words, and these initial vector representations, they are combined or aggregated. Usually some kind of hyperbolic tangent function is used to aggregate those context vectors to obtain the vector representation of vi. And these vectors, the neighboring vectors, sometimes we call them contexts. On the other hand, in the skipgram model, in the skipgram model, the distributed representation of the input vector, this is distributed to the context vectors. So these are two shallow neural network models, and there are other techniques that use this kind of network also existed before, but they are computationally expensive. But so this skipgram and continuous bag of word model, they were popular because they were also very computationally efficient. So the question is, I mean, if we employ this word2vec that basically makes a distributed representation of the code, are they good for source code analysis or not? So in order to understand that, a two-dimensional representation of code tokens that is learned from 6.3 million lines of C and C++ codes are drawn here. And if we look into it, for example, then we see that similar tokens are clustered together. For example, if you see these types, Boolean, new, string, they are clustered together here. Or if you see free, delete, they are together here. For example, calloc and realloc, they are here. So we see that, I mean, this word to bake can also learn important features of the code, and they are applied to solve many software engineering tasks using neural networks. So there are, yeah, I think I have only few minutes left, right?
Yes.
Yeah.
4 or 5 minutes.
4 or 5 minutes. Okay. Okay. So there are other representations. So we have two important observations for the code to bake. So first observation is that even though we have seen good clustering of source code tokens of the word to bake representation, but important semantic information of the code may not be captured if we treat the programs as natural language texts. And the second observation is that syntactic structure can provide better representation than token-based method in modeling source code. So based on these two observations, code to bake is introduced. Which basically represents source code using abstract syntax tree. To give an example, consider this max function that basically calculates the max of two numbers a and b, two parameters a and b, and we have an abstract syntax tree representation here. So the root function is the function declaration of the max, and it has the param declaration. These two param declaration represents the two input parameters of the max functions, and then the compound statement represents the body of the max function. This compound statement has also if statement and return statements like this if and this return. So this kind of abstract syntax tree can be generated using by the parser. So this code to bake, what it does is it generates AST path from one terminal node. All the leaf nodes are the terminal nodes. So it generates AST paths from one terminal to another terminal like this, and then it generates a vectors of this AST path. So because and this is done by means of assigning initial random vectors to the terminal nodes and use some kind of tree-based neural network to learn the vector of this context. We call the middle nodes as contexts. So these are the contexts. So in this way, we can get the vectors of this AST paths. Then the main idea is then to decompose the code snippets into a number of AST paths from one terminal to another terminal and represent them as bag of distributed vector representations, and finally use an attention mechanism to compute the learned weighted average of the path vectors in order to produce a single code vector. For example, we can see in this figure, this is the architecture of this kind of learning techniques. So the input of this architecture is these context vectors of AST paths that we have seen before, and the three dot represents three vectors. This first one is, for example, for the first terminal, the last one is the last terminal, and the middle vector represents the vectors of the context. So these context vectors are then combined or concatenated in the fully connected layer, and these vectors are also then they are sent to the attention layer to learn the what it does is to learn the weighted average over the combined context vectors and compute a scalar weight for each of them. So then the aggregated code vector, then this code vector, they are aggregated. They are then what is done is that basically the scalar weight basically then and these code vectors weights, they are then linearly combined to obtain the code vector, which is later softmax normalized. So this is the typical procedures to get an to get a how is it called final representation of the source code from the AST tree. You can see the code to bake papers to see the details of all the steps. So this is one kind of representations of AST-based representations to represent the source codes. But its limitation is that it has the vanishing gradient problem, especially if the AST is very large and deep. And this usually happens for most typical C and C++ or Java repositories. Another problem is that they rely on the generation of the vectors of the AST contexts, and to generate the AST context vectors, they typically view the AST as full binary trees, and then these full binary trees basically make the AST even more deep, and then even make the vanishing gradient problem even deeper. And to solve this problem, another technique, for example, ASTNN, which is abstract syntax tree-based neural network, is developed, which basically split the abstract syntax tree into multiple abstract syntax tree, or we can call a statement tree, which are by the statement encoder, which is converted to vectors. And then these vectors are passed through this bidirectional recurrent unit, and then it is pooling is used to transform this encoding into how is it called, into AST representation of the whole code. So this is another way of doing that. So there are many more techniques. For example, there are also techniques to represent control flow graphs or control and data flow graphs to vector representation of those graphs. So, but then there are some open challenges in neural software analysis. So until now, neural analysis of software tasks have mostly influenced by the available datasets, and some tasks have received very little or no attention from the neural software analysis community. Those includes, for example, performance properties of the software, automated test input generation, or automated fault injection, or performance regression for code changes. This kind of tasks have not given much more attention yet. A core concern of every neural software analysis is how to represent the software as vectors that enable the neural model to reason about the software. So learning code representation, it is an active field of research, and probably we will see many more representations because more sophisticated software analysis that are being done by static or dynamic analysis are not yet done in neural software analysis. So and the success of those kind of sophisticated analysis depends on how better we can represent the code. So then the third challenge is how can we interpret the prediction of the that the neural software analysis gives us. This neural, I mean, this is like in any other domain. Neural models, they suffer from lack of interpretability, and the consumers of neural software analysis is basically software developers. So future research should investigate why a model makes a prediction and how to give developers more confidence in following the prediction of a neural software analysis. Then neural and traditional analysis techniques have complementary strengths and weaknesses. So for many problems, maybe it is best to combine both methods to get a more effective results. And then scalability is an important issue also for neural software analysis. So far, most neural software analysis, they are focused on a small code snippets, maybe at most a single function they focus on. So future work should investigate how to make predictions about the large pieces of code, for example, the entire modules or the applications, and how to do it in a more efficient way. Then in this talk, we have mostly focused on the source code, but there are other artifacts of software, such as, for example, the code comments, the software generated artifacts such as crash reports or logs or this kind of artifacts. Maybe it is better to combine both source code and this kind of artifacts to solve many of the software engineering tasks. So that's all from me for today, and I am just working recently on this topic. So I'm also looking for collaboration. So if you want to work on this area and want to collaborate with me, please contact me. Thank you everybody for your attention.